Welcome to the Deep Dive. We're the podcast where we really get into the details, pulling out the key insights from interesting sources for you. Today, we're pulling back the curtain a bit on the, let's call it magic, behind these super powerful AI models everyone's talking about, things like ChatGPT. And there's actually a surprising truth hiding in plain sight about how they're built. We're diving deep into this really fascinating link between the transformer architecture, the one powering those big language models, and something called graph neural networks, or GNNs. Our guide for this is a pretty compelling paper by Chaitanya K. Joshi, The Big Claim. Transformers are graph neural networks currently winning the hardware lottery. So our mission today is to unpack that. What does it mean? How do these two things connect? And what's this about hardware playing such a big role in which AI ideas take off? If you've ever wondered, what actually makes these AI breakthroughs tick, or how machines process really complex stuff, well, you're probably going to have a few aha moments today. Okay, so let's unpack this. Before we even start connecting transformers to GNNs, we probably need a quick refresher on what transformers are and why they kind of took over. Fundamentally, a lot of machine learning boils down to this idea of representation learning. You're basically trying to squish down raw data like text or images into these dense numerical lists, embeddings, they call them, that capture the important stuff, the semantics, the statistics.
Exactly. And good representations are key, right?
Yeah.
Because they let the model generalize. It can take what it learned in one area and apply it somewhere else, kind of like how learning math might help you with programming. And specifically in NLP, natural language processing, there's been a huge shift. For ages, RNNs, recurrent neural networks, were the standard. They worked sequentially. Like a conveyor belt, as you said earlier, processing words one after the other, building up context.
Yeah, but that step-by-step thing had limitations, didn't it? Especially with longer pieces of text, they had to kind of cram the meaning of the whole sentence into one fixed-sized chunk of numbers at the end.
That's right. They struggled with long-range dependencies. Remembering something from the beginning of a long paragraph was tough. Then came the attention mechanism. Even before the full transformer, it was a way to let RNNs sort of look back at important words in the input, not just the last one they saw.
Okay, so attention started as a fix for RNNs.
But then transformers arrived and really turned the whole thing on its head. They took that attention idea and ran with it. Instead of processing sequentially, transformers build representations for every single word in parallel, simultaneously.
In parallel, how does that work?
Well, each word basically looks at every other word in the sentence, including itself, and calculates how important each of those other words is to understanding it. Then it updates its own representation based on a weighted combination of all the other words' information.
So every word is talking to every other word at the same time.
In a computational sense, yes. That parallel nature and the ability to directly link words far apart, that's what gave them their power, their expressivity. And, crucially, their scalability. They just blew RNNs out of the water for most NLP tasks, and then started spreading everywhere else.
And wasn't there a practical reason, too? Like, training RNNs was just getting too slow?
Oh, absolutely. Part of the motivation at Google, where transformers originated, was precisely that. Training RNNs on their massive translation data sets was incredibly inefficient. They needed something faster, something that could handle more data. Transformers fit the bill.
Okay, so let's get into that core mechanism then, the attention. You mentioned query, key, and value.
Right. So for each word or token, the model learns to generate 3 different vectors, basically just lists of numbers, through linear transformations. These are the query Q, the key K, and the value V.
Okay. Query, key, value. What do they do?
Think of it like this. If a word wants to update itself, its query vector goes out and asks, who has relevant information for me? It compares its query vector to the key vectors of all the other words in the sentence, usually using a dot product. High dot product means high relevance or alignment.
Got it. So the query asks, the keys answer how relevant they are.
Exactly. Then you take all those relevance scores, run them through a function called softmax, which just turns them into nice weights that add up to 1. These are the attention weights. They tell you, for this specific word, what proportion of attention it should pay to every other word, including itself.
And the value vector?
The value vector holds the actual substance, the information that a word wants to share. So the final updated representation for our word is a weighted sum of all the value vectors in the sentence, weighted by those attention scores we just calculated.
Okay. So query asks, key says how relevant I am, value provides the what I know, and the attention weights decide how much if-she value gets mixed in.
You've got it. And the beauty is this whole QKV calculation and the weighted sum happens in parallel. for every single word in the sentence, all at once. One big shot. That's the parallel power compared to the one-by-one RNN.
But just one set of QKV might be limiting, right? Words relate in different ways.
Absolutely. Syntax, semantics, just context. A single attention calculation might miss some nuances. That's why they introduced multi-head attention.
Multi-head. So multiple sets of QKV.
Exactly. The model learns several sets of QKV transformations independently. Each head performs its own attention calculation in parallel. It's like looking at the sentence through multiple different lenses simultaneously. One head might focus on grammatical links, another on semantic similarity, and so on. It lets the model capture a richer set of relationships.
And then you combine the results from all these heads.
Yep. You concatenate the output vectors from all the heads and then usually project them back down to the original size with another linear layer. And critically, all of this calculating multiple attention heads in parallel maps beautifully onto modern hardware. It's basically a series of large matrix multiplications, which GPUs and TPUs are incredibly good at crunching through very, very quickly.
Okay, so multi-head attention gives it depth.
Go ahead.
What else is in a standard transformer layer?
So after the multi-head attention does its thing, you typically have a couple more standard deep learning components. First, there's a residual connection. You basically just add the original input representation from before the attention step back to the output of the attention step.
Why add it back?
It helps with training, especially in very deep networks. Prevents gradients from vanishing, makes it easier for information to flow through many layers. Then there's layer normalization, which also helps stabilize training. And finally, the output goes through a token-wise multi-layer perceptron, or MLP. It's sometimes called a feed-forward network.
Token-wise, so each word's representation gets processed independently by this MLP.
That's right. It's like a little neural network applied to each token separately, allowing the model to process the information gathered by the attention mechanism in a more complex way. And it's worth pointing out, these MLPs often contain way more parameters, the learnable knobs of the model, than the attention mechanism itself.
Interesting. So attention gets the context. MLP processes it further for each word.
Sort of, yeah. And these components, the multi-head attention, the residual connections, layer norm, the MLP, that whole block is a single transformer layer.
Right.
And you stack these layers one after another, sometimes dozens or even hundreds of times, to build these huge, powerful foundation models we see today. Okay, now let's completely switch gears for a moment. Let's talk about graphs. Think about data that isn't just a sequence, but has a relational structure, sets of things with connections between them. Graphs are literally everywhere. You mentioned social networks, people are nodes, friendships are edges, knowledge graphs connecting facts. Molecules, atoms are nodes, bonds are edges. The web itself is a graph.
Right. Nodes and edges. Pretty simple concept. And you said earlier they have this permutation symmetry. What does that mean exactly?
It just means there's no inherent order to the nodes. If you have a graph of 3 friends, it doesn't matter if you list them Alice, Bob, Carol, or Carol, Alice, Bob. It's the same set of connections, the same graph.
Ah, okay. Unlike a sentence where word order definitely matters.
Precisely. And graph neural networks, GNNs, are designed specifically for this kind of data. They have to respect that permutation symmetry. GNNs are deep learning models built to work directly on graphs. They use the graph structure, the connections, to figure out how information should flow and combine. They're used for all sorts of things, like predicting molecule properties or recommending friends on a social network.
So how do they actually work? How do they use the structure?
The core principle is usually something called message passing. It's an iterative process. For each node in the graph, it does roughly 3 things in each layer. First, message construction. Each node looks at its direct neighbors. For each neighbor, the node and the neighbor construct a message. This usually involves their current representations, maybe edge features, processed by a small neural network.
Okay, so nodes create messages for their neighbors, like passing notes in class.
Kinda. Then step 2, aggregation. A node gathers all the incoming messages from its neighbors. Since the order of neighbors doesn't matter, permutation symmetry, it has to combine these messages using an operation that doesn't depend on order. Things like summing them up or taking the average or the maximum value.
So sum, mean max, they give the same result regardless of the order the messages arrive in. Makes sense.
Exactly. This gives you one single aggregated message representing the combined wisdom of the neighborhood. And step 3 is update. The node takes its own previous representation and this aggregated message and combines them, usually using another small neural network, to compute its new representation for the next layer.
Message, aggregate, update.
And you stack these layers.
Yes, stacking layers allows information to propagate further. After one layer, a node knows about its direct neighbors. After 2 layers, it knows about its neighbor's neighbor, and so on. You capture these multi-hop relationships. Now, within GNNs, there is a particularly relevant type called graph attention networks, or gates.
Attention again? Okay, so how does attention work in graphs? Well, remember in the aggregation step, we just summed or averaged messages. GATS thought maybe not all neighbors are equally important. So GATS use an attention mechanism, much like the one we discussed for transformers, but locally. When a node aggregates messages from its neighbors, it calculates attention weights to decide how much importance to give to each neighbor's message.
Ah, so instead of just averaging, it's a weighted average, where the weights are learned based on relevance.
Precisely. It learns which neighbors are more important for updating a specific node in a specific context. And, just like transformers, GATs often use multi-head attention too, letting them learn different types of neighborly importance simultaneously. And get this, when you look at the equations for how GATs compute those local attention weights, they should look very familiar.
Okay, I think I see where this is going. So the paper's big claim, transformers are graph neural networks. That sounds huge. It reframes how we should think about them, doesn't it?
It really does. It's not just an analogy. The argument is about a formal equivalence, at least under certain conditions. The core idea is this. You can view a standard transformer as a specific type of GNN that operates on a fully connected graph.
Fully connected, meaning every node is connected to every other node.
Exactly. In a transformer processing a sentence, think of each word, token, as a node. The self-attention mechanism calculates the relationship, the attention weight between every pair of words. That's equivalent to message passing on a graph, where every node has an edge to every other node.
Okay, wow. So the transformer's global attention is just GNN message passing on a complete graph.
That's the argument. If you write down the math for the transformer's multi-head self-attention, the Q, K, V, the dot products, the softmax over all tokens, and compare it to the math for a graph attention network, GT, performing message passing.
They're the same.
Almost identical. The fundamental mechanism is the same. The GAT applies it only to neighbors defined by the input graph structure. The transformer applies it to all other tokens as if they were neighbors in a fully connected graph. The final equations used to update the node token representations are essentially identical in form.
So what does that imply if transformers are GNNs on complete graphs?
Well, it means transformers are incredibly expressive set processing networks. They aren't limited by a predefined sparse graph structure. They can potentially learn any relationship between elements in the input set, whether local or global. This is super useful when you don't know the underlying structure beforehand or when long-range interactions are really important. Think about protein folding atoms far apart in the sequence can end up close together and interact strongly in the 3D structure. A standard GNN might struggle if those atoms aren't neighbors in the initial graph representation, but a transformer can learn that interaction directly.
That makes sense. So it gives them flexibility.
Huge flexibility. And you can flip it too. You can see GATs as being like transformers, but where the attention is deliberately restricted or masked to only operate within local neighborhoods defined by the graph. It's like sparse attention guided by the graph structure.
Has this connection led to new types of models?
Oh, absolutely. It sparked the development of graph transformers. The idea is to try and get the best of both worlds. Remember how transformers use positional encodings to give the model a hint about word order? People realized you could do something similar. For graphs, create encodings that give the model hints about the graph structure, like a node's distance from others, or its role in local motifs.
So you feed structural information into a transformer architecture.
Sort of, yeah. You softly inject graph structure information, often via these positional or structural encodings, into a powerful transformer block that can still perform global attention. The goal is to combine the GNN's strength in leveraging local structure, its inductive bias, with the transformer's ability to capture global dependencies and its proven scalability. It's a very active area of research.
Okay, this is fascinating. But it leads to the big question, the one raised by the paper's title. If transformers are basically GNNs, why are transformers everywhere? Why aren't we talking mostly about GNS winning?
This is where the hardware lottery comes in, right?
Exactly. This concept, the hardware lottery, suggests that it's not always the theoretically best or most elegant idea that wins out in practice. It's often the idea whose computational needs happen to align well with the capabilities of current hardware.
So it's about efficiency. How do transformers and GNNs differ in terms of how they run on, say, a GPU?
It boils down to dense versus sparse operations. Transformers, with their global self-attention, perform their core computations using dense matrix multiplications. Multiplying large matrices together is something modern GPUs and TPUs are highly optimized for. They have specialized cores designed just for that. It's incredibly parallelizable and efficient.
So the transformers math just happens to be exactly what the hardware is good at. Pretty much, yeah, it's a perfect match. Now contrast that with typical GNNs. They perform message passing over sparse graph structures. A node only interacts with its immediate neighbors, not everyone. Computationally, this involves operations often called gather and scatter. You need to gather information from specific, potentially scattered memory locations, the neighbors, compute messages, and then scatter the updates back.
And that's less efficient on a GPU.
Substantially less efficient for most typical graph sizes. GPUs prefer operating on large, contiguous blocks of data, like dense matrices. Handling sparse, irregular memory access patterns is much slower. There are exceptions for extremely sparse graphs or truly massive ones where specialized systems come into play, but for many common tasks,
GNNs are just slower.
orders of magnitude slower to train, often, and harder to scale up effectively on the kind of hardware most researchers and companies have readily available. The engineering effort to optimize sparse GNN computations is significant compared to just using highly optimized libraries for the dense matrix math and transformers.
Wow, orders of magnitude. That's a huge practical difference.
It really is. And what's maybe even more surprising is that evidence suggests that if you train a big enough transformer on enough data, it can actually learn the kinds of structural patterns or inductive biases that are explicitly built into GNNs, like locality.
So the transformer can learn to act like a GNN if needed, given enough scale.
It seems so, especially if you give it those hints we talked about, like appropriate positional or structural encodings. You're not forcing the structure on it architecturally like a GNN does, but you're giving it clues, and its powerful attention mechanism can figure out how to use them. So you put it all together. Transformers have this universal approximation capability via global attention, they can learn structural biases, and they run incredibly efficiently on current hardware.
Whereas GNNs, while perhaps theoretically elegant for graph data, face practical hardware hurdles.
Exactly. Which leads directly to the paper's conclusion. Transformers are, in a sense, graph neural networks. But they're the ones currently winning the hardware lottery. Their expressivity, flexibility, and crucially their hardware efficiency make them the dominant architecture for now.
And that brings our deep dive to a close. What a journey. We started with understanding transformers, their rise replacing RNNs thanks to parallel attention. Then we explored graph neural networks, how they use message passing on structured data. Then came that really mind-bending connection, seeing transformers as GNNs operating on fully connected graphs. And finally, the crucial role of the hardware lottery, explaining why the transformer's dense computations give it such a practical edge right now. So, what's the big takeaway for you listening in? You've just got a glimpse into this really deep relationship between architectures that seem different on the surface, and you've seen how practical things, like how well an algorithm runs on a GPU, can fundamentally shape the direction of AI research. It really drives home that point, doesn't it? The future of AI isn't just about clever algorithms on a whiteboard. It's this constant dance between the theory, the mountains of data we have, and the actual silicon chips we designed to process it all. Which leaves us with a thought to chew on. If transformers won this round of the hardware lottery, what happens next? If new hardware emerges, maybe optimized for sparse computations, or something completely different, could the winners change? What might the next dominant architecture look like?